In chapter 1, we would like to introduce the idea of electromagnetic fields and electromagnetic waves. So first of all, we would like to establish the concept of fields. So for your information, field is in the form of vectors. So it has dependence on 3 dimensions. And because electromagnetic fields are time-variant functions, so electrical field and magnetic fields in general are dependent of 4 parameters, 3 dimensions in space and 1 dimension in time. And of course, the important thing about the study of electromagnetic waves is the so-called Maxwell equations. So we will spend certain amount of time in chapter 2 and 3 for the introduction of Maxwell equation. And for the study of electromagnetics, the vector analysis is the most fundamental mathematical tools. So in chapter 1, we will review some important mathematical tools associated with the study of electromagnetic wave, including the concept of coordinate systems. We will not only introduce the Cartesian coordinate system, which is the rectangular coordinate system x, y, and z. We will also review the so-called cylindrical coordinate system and spherical coordinate system, 圆坐标球坐标跟柱坐标系统which are easier to describe the problem in space. And you need to get accustomed to the ideas of scalar fields and the vector field, 存量向量, and the static field and time variant field, 进场跟时变场, 进场跟时变场. And first of all, we will introduce the Coulomb's law and Ampere's Kirchhoff law, which is directly associated with electrical field and magnetic field. Then we will look into the so-called Lorentz equations that associate the time variation between electric and magnetic fields. And here's the relationship of the agenda of chapter 1, which you can look up to yourself. So in the study of physics, some quantities are associated with length, not only a magnitude. Of course, you have already learned physics, and there are parameters involved in the study of physics. And many times we will bump into parameters that not only associate with magnitude, but also associate with direction. For example, speed. Of course, you need to describe the amount of speed, and more importantly, you need to describe the speed as a, you need to specify the direction of the speed so that you can predict or estimate the moving directions or the moving status of the object. So they are referred to as vectors. So on the textbook, you should, I would like to point out the difference in the vectors and scalars. 搞清楚这两个差异在课本上的差异我大学的时候电磁学一学期都快念完了，我才发现这两个东西是不一样的一个是存量，一个是向量The vectors are printed in boldface Roman, so they are wider, bolder in the, and the scalar are printed in wide face italic, like this. So it's critical for you to differentiate between scalars and vectors. And from my own perspective, when I grading the exams, one of the things that I cannot tolerate is you mix up the idea of vectors and scalar。所以基本上我在改考卷的时候，大概尽量保持佛心啦，但是我自己没办法克服的一点就是你在向量跟存量搞不清楚的时候，所以教你向量跟存量，好啦，课本的话当然它有所谓的 boldface 跟 lightface italic 的区别嘛，那在写的时候，向量你就记得加一杠杠嘛，上面一个箭头，但注意你尽量不要写成这样子。因为这个东西在电磁学里头，它还有另外一个意义，它指的是 phaser。phaser， 我们现在还不会碰到了，但后面会碰到 phaser 这件事情。这个是 vector。还有，请你尽量不要把一个向量写成这样子。请你麻烦一点写成。尽量写完整。我一般都讲说，电磁学的数学不难，它只是比较烦，因为一个式子你要写3遍，因为它是3个 dimension 3维的，它真的只是比较烦它其实不难，好不好？尽量不要对电磁学的数学有太大的恐惧，好不好？尽量不要写这一种的，好不好？写成这个样子的，你写成这种的话，就要改分数的时候就要看我心情了，心情不好就杠掉了OK， 写这样就没问题 ，OK， Alright, so a vector can know because it has direction and magnitude, so it can be represented graphically. So on the slide, you can see there are 4 vectors, so it's kind of intuitive. The size of the arrow, the arrow represents the direction of the vector. The size of the arrow describes the magnitude of the vector, and the direction represents the direction, right? So it's kind of an intuitive representation for graphical. For describing the vectors graphically. And in a 3D environment, we will need 3 reference directions. So as I write on the blackboard, what is AX, AY, and AZ? They are the so-called reference direction. And X, Y, Z suggests that I'm describing the vector in the Cartesian coordinate system, 直角坐标系统。Cartesian coordinate system. And of course, we will have cylindrical and spherical coordinate system. And the reference direction, which are shown as AX, AY, and AZ with an arrowhead above, suggests its direction as well as its magnitude, which is 1. So AX, AY, AZ over there are the so-called univector, which has a vector or magnitude of unity, 大小为一 So in print on the textbook, it's written as a bold-faced Roman like this, and in writing you can write it as this, or you can use a subscript 下标 to denote the direction. All right. So you have AX, A, X, Y, and Z are the subscript that describe the direction of the univector. And the importance about the study of electromagnetics is we adopt the so-called right-hand screw, 右手系统 So, of course, you know that in the Cartesian coordinate system, you have X, Y, and Z. And the order is important. The XYZ order is important because if you have a cross product, YG cross product, say AX cross AY, the direction is AZ. On the other hand, if you do the product, cross product as AY cross AX, what is the result? Well, the result is minus AZ. So the order of your cross product will change the sign of the result. So you need to be sure that the order of your unit vectors follows the right-hand screw systems. So in this one, A1 cross A2, using the right hand, you end up with the A3 direction, which is pointing upwards. On the other hand, if you adopt a left-hand system, then A1 cross A2 will end up with this direction. So that's the left-handed systems. Okay, so forget about the left-handed systems. We always adopt the right-handed system in electromagnetics in most engineering courses, I guess. All right. So usually you use right-hand system to do the cross product. All right, and the concept shown here is the representation of vector, which means that a vector which can be pointing arbitrarily in the space, and their projection, they can be described as a sum of reference directions. So for example, here you have 3AX plus 4AY plus 5AZ. So this is the whole description of the vector, and they are. So what is the significance of 3, 4, and 5? They are the projection on x direction, y direction, and z direction respectively. So vector can be expressed as the sum of its projection on the 3 reference direction. Okay, so the plus sign here is not that directly related to arithmetic operation. It's just an association that describes the 3 things are used jointly to describe vector in the space. So don't look it up as a sum, okay? It's just an association. 所以向量可以被拆解成参考方向上面的投影量所以这个加号不是那个传统意义上的算术上面的加啦但是就是一个连结的表示所以向量我们在一般表示的时候，就根据你的坐标系统去用它的投影量，还有那个 reference direction 参考方向上面的描述来去标示它，好不好 ？So what is the magnitude of this vector? Well, it's the square root of its square sum. Now, as you already know, that it will be 3 to the square plus 4 to the square plus 5 to the square. And taking the square root of that will be the magnitude of this thing. Okay. And here are some illustration of the concept of the projection of a vector on the 3 reference direction. Alright, a vector at a given point is simply the superposition of the 3 vectors on the reference direction. So this is kind of another elaboration of what I've just explained. So for any vectors, say A, vector A, in equation 1.1, it can be decomposed into A1, A1 plus A2, A2, and A3, A3. So the 3 this is the vector. The 3 scalar represents the magnitude of its projection on A1 direction, A2 direction, and A3 direction. 所以这边稍微注意一下这个是向量 ，A1 是向量，这个是向量，这是向量，但这个就变存量了。这是存量。注意一下它们的表示方式。 Okay? And you can write up the vectors, other vectors in a similar fashion. And now let's review some of the simple vector operation. The first one is vector addition. I suppose that you can do that very easily. Vector subtraction, well, it's in principle the same as vector addition, all right, even though that you have a minus sign over layer. So as you can see from the two equations that the addition and subtraction can be done with the so-called 分配率嘛，OK， 你可以把它们在各个向量上面的参考方向上面投影量去个别做相加或相减嘛，所以这称之为分配率And multiplication 乘法注意一下这边的乘法是专指向量跟一个存量的相乘。那我们在做向量的我们还有向量跟向量的相乘。向量的相乘又分为内积跟外积你以前学过的dot product and cross product 但这边的话，这边的乘除是 multiplication 跟 division 它指的是向量跟存量之间的相乘或相除的操作跟接下来我们要讲的 cross product dot product 不太一样不一样，不是不太一样，是不一样 alright? Okay, so as the equation shows, the multiplication and division with a scalar can be done easily by taking the multiplication individually in the projection on the three reference direction, like well, as the equation suggests. Next is the calculation of the magnitude of the vector. As I already pointed out, it's the magnitude can be found by taking the square root of the square sum of all three projections, like this. A1 to the square plus A to the square plus A3 square, and taking the square root of that. And 1.A, equation 1.A shows you how to derive the so-called unit vector. That is a vector that is aligned with the vector A, but with a magnitude of 1. This is the so-called unit vector. The unit vector is not necessarily pointing to the reference direction. It can be pointing to any direction. So the derivation of the unit vector. So if you come up with this sign, lowercase a in boldface, that suggests this is the so-called unit vector. So its magnitude is 1, and the subscript describe the direction. So that will be, so this will suggest the unit vector of the vector A, which can be found by taking the division of the vector A itself with magnitude, with its magnitude. So that will be A divided by absolute value of A. And more conveniently, it can be expressed as the sum of its projection in the three reference directions. So here you have the unit vector for the three reference direction, A1, A2, and A3. And the projection of A on the three reference directions, which are A1, A2, and A3, divided by the magnitude of A will be its projection of the unit vector along the three reference direction. So be acquainted with this description, the unit vector of arbitrary vector. Right? Okay, and next we will discuss the two more important operation of vectors. They are the so-called dot product. 中文叫内积了我比较常讲叫内积了但英文好像没有 inner product 这个用法了其实就叫 dot product So it's written as A dot B. So it's simply finding the projection of one vector onto the direction of the other vector. So this will be the product of, so look at these three graphical representation carefully. So if you draw the things in this way, you are first calculating the projection of vector B on the direction of vector A. So graphically, that projection, which is this distance, will be B cross cosine alpha. Alpha is the angle between the two vectors. So the smaller the angle alpha, the larger the projection of vector B on vector A. So here is the projection of B on the A direction, and the dot product will be the multiplication of B cosine alpha times A. And this expression suggests we are looking at the projection of vector A onto the direction of B. So it's written as A cosine alpha times B. So the result is the same, but the implication, 它们的结果是一样的，但是思路不太相同，好不好？这两种写法思路不太相同And here's the addition of the vector. Okay, and mathematically, the dot product A dot B can be expressed as the product of the magnitude of a vector A and B times cosine alpha. And as you know, if alpha equals to 0 degree, what is cosine alpha? Cosine alpha becomes 1 if alpha is equals to 0 degree, and cosine alpha becomes 0 if alpha is what? 90 degree, right? If alpha is 180 degree, cosine alpha becomes -1. All right, so the dot product is larger if the two vectors are nearly aligned to the same direction. 所以对两个向量来讲，它们的夹角越小，那它们的内积就越大。当它们的夹角越接近90度，那它们一个向量在另外一个向量的 projection 越少，那内积的结果就越小，对不对？所以Okay, so on the top of this, on the top shows the unit product, dot product of the unit vectors. So, as I already mentioned, if the two vectors are linear orthogonal, the dot product of the two becomes nearly 0. Orthogonal, 什么是 orthogonal? 垂直啦，垂直还有好几种讲法 ，perpendicular 也是垂直啦 ，orthogonal 也是垂直嘛，所以两个向量假如接近垂直的话，它们的内积dot product 就趋近为0。所以你今天假如把 reference direction unit vector of the reference direction 做内积的话，你会发现。A1 dot A1 equals to 1, A1 dot A2 equals to 0, A1 dot A3 equals to 0. So only the diagonal terms of the matrix of the product of the two reference direction becomes 1. 所以只有在同方向的向量，它的内积会等于1啦垂直的向量就等于0所以这边带到坐标系统，参考坐标系统里头的参考向量的一个重要特性，也就是 对于一个坐标系统来讲，它的3个参考向量 reference direction are perpendicular to each other. They are orthogonal to each other. The inner product of the reference direction always equals to 0. So that's one of the required properties for reference direction in a coordinate system. All right? And down below is the property about dot product. So here you see B dot A equals to A dot B. So this property is referred to as the commutative property. So you can change the order of the two vectors involved in the dot product, and the result is the same. So dot product has the so-called commutative property, which is not true for cross product. Here is the property about another property about dot product, that is the distributive properties. So if you do A dot B plus C, you can do A dot B and A dot C separately, and then combine the result on the reference direction, and the result are the same, right? Okay, and over here is another reminder about the orthogonal property of a reference direction. Okay, so here are some operating principles about the dot product. And you can simply taking the product of the two vectors in each reference direction. So A1 dot B1 plus A2 dot B2 plus A3 dot B3 end up with the dot product result. And here's another important property that I need you to memorize is what is the property of vector dot product? It becomes a scalar. The dot product of two vectors is a scalar. 所以今天你最要能够记起来的收获就是搞清楚向量跟存量，好不好？向量跟存量搞清楚。向量的内积，它的结果是存量。OK， 有没有看到前面的这些结果？它其实都是存量，就是说，你的那个 A1 跟 B1 乘起来之后，它就变成一个存量，没有方向性。那 A2 跟 B2 乘起来之后也是存量 ，A3 乘 B3 也是存量，所以它们3个是可以被加在一起的，加在一起的。Right, and alpha, as already mentioned, that is the angle between the two vectors, which can be found using the definition that by taking the arc cosine 注意这个念法叫什么 ？cosine 不是 cosine 负1要念什么 ？arc cosine ARC arc cosine arc cosine 指的就是 cosine 的那个反函数负1次方。So alpha is the arc cosine of r dot A dot B divided by the product of magnitude of A and B. Right, so which can be expressed in this way. Okay. So, as already mentioned, if the two vectors are perpendicular to each other, are orthogonal to each other, 互相垂直的话, the dot product becomes 0 for any two vectors, if they are perpendicular to each other. On the other hand, if you found that the dot product of the two vectors equals to 0, then you can conclude they are perpendicular to each other, right? And next is the vector, the cross product, 外积 cross product. And the cross product is written as A cross B. 所以在课本里头你假如是乘法的话常看到的一种写法其实是这一个星号。这个话你看到这个你大概就知道是乘法。multiplication， 但你看到这个的时候要小心它可能指的是 cross product，OK， 在我们这本课本里头要注意这个符号只要你看到一星号，那其实就是简单的 multiplication但这个话指的是 cross product 外积 So 好吧，先讲一件事情 ：the cross product of two vectors is a cross product， is a vector 啊，向量的外积还是外积哦？向量的内积是存量，向量的向量的外积还是向量？向量的内积是存量。OK， 好 ，that's the most distinctive difference between dot product and cross product. The cross product of two vectors, the cross product, of course, cross product operates on two vectors, and the result is also a vector, all right? And mathematical expression, it can be shown as A cross B equals to the multiplication of the magnitude of A and B times sine alpha. And it comes with a description of direction, AN. N stands for normal direction. Normal direction 什么意思？正交的方向。normal direction 正交方向。所以这个 AN 呢，它其实有一个重要的性质，就是它跟 vector A 是垂直的，它跟 vector B 也是垂直的。所以基本上，假如说你有两个向量。它们这两个向量张开在一个平面上，比如说是黑板好了。那么 A cross B 的结果，用你的右手比一下，会出来在哪里？会出来在这个方向，而这个方向呢，会跟这个平面是正交的。所以 cross product 也可以让你找到任意两个向量的张出的平面的法线方向。所以 normal direction is also refers as 法线方向 ，OK 就法线方向就是 normal direction，OK Alright, so this representation comes like this. Here's the magnitude AB times sine alpha. As you can see here, there are scalar. This is a scalar, but it comes with AN, which turns it into a vector. Alright. And because the magnitude of the cross product is associated with the angle alpha, and it's in the relationship of sine, so what is the implication? If the two vectors align to the same direction, then the cross product is nearly zero. If the two vectors are perpendicular to each other, then sine alpha becomes 1. So you will get maximum value with the cross product. Alright? And as a result, if you take in the cross product of the unit vectors in a reference coordinate system, you found that A1 cross A1, the cross product of the vector itself becomes 0. And the cross product of two different reference direction, the magnitude is 1, but you need to be aware of the relationship, the order. We know, as I already mentioned in the beginning of the class, I say you need to be aware that they are in the order of the right-handed system. So 1 cross 2 end up with direction of 3 in the positive direction. If 2 cross 1, then you will end up with 2 cross 1. Who is 2 cross 1? Okay, will be negative A3. So be sure to remember the order. And you can do that with your right hand. Okay? So cross product do not have the so-called commutative property. So B cross A will be minus of A cross B. However, the vector cross product still holds the distributive property. So you can do the cross product separately. So A cross B plus C equals to A cross B plus A cross C. So, and here shows that the cross product is still, the cross product of two vectors is still a vector. So you end up 3 terms in the 3 reference direction. Near to be, well, it's probably a little bit difficult to memorize this order. So in practice, the more common practice is to perform the cross product in the so-called determinative form. Determinant form. So you, I suppose, 有学过吧? So that will be, in the A1 direction will be A2 times B3 minus A3 times B2, and for the A2 you will have A3 times B1 minus B3 times A1, okay. And so here's the representation to find out the normal vector. So you can use this property to find out the normal product because the cross product will be perpendicular to the two vectors involved in the problem. 好吧，我们今天先到这边吧。OK， 那张表写完了，你们这边有签了吗？我看一下。好，我们今天到。